we have one final task for this section. So let's look at a picture of a scenario, and hopefully this will enlighten what this last task is. So we have a plane sitting out here. Let's call it pi. Right? So I have my cool little plane here, and floating somewhere around in space, I have a point. Let's call it P. Right? I want to know what is the shortest distance between this plane and P. Well, think carefully about this. And let's think about it using sort of an analogy here. Imagine this plane is a basketball court, and P is the hoop. Right? Where do I have to go so that, or where should I jump from? Where should I jump from so that I can reach the hoop covering the least amount of air distance? Well, it should make sense that if you want to cover the least amount of distance, you should stand directly underneath the hoop to jump up and grab it. Right? That's the shortest amount of air time required. Otherwise, not only do you have to jump up high enough, but you also have to jump out far enough. So it should make sense then that to get the shortest distance, we just want to drop a line here. Let's make it bold. That's perpendicular to the plane. Right? And let's even cut this a little bit here to show that that line's really coming off of the plane. It's perpendicular to it. But if the line is perpendicular to the plane, well, what does that mean? That means the direction of this line segment here is the normal vector to the plane. All right. So that solves that problem. The shortest distance from the plane to the point is a perpendicular line connecting the plane to the point. But it's kind of hard to choose precisely the point right underneath P. So what can we do to get at that? Well, what it is really easy to do is to just pick any old point, Q, on the plane. We might get lucky and actually choose the point down here, but chances are we're going to choose something that's off somewhere. So let's say we've done that, because we probably have. How can we fix that? What can we do? Well, we now have a connection we can establish between the plane and the point. And that's this displacement vector here, QP. Right? We now have a connection between the plane and the point. What good does that do us, though? It actually does us a whole lot of good. Because, well, what that actually allows us to do is get a vector in the direction of n connecting the plane to P. Do you guys remember how we might be able to do such a thing? Think about that for a second. Well, what we can do is take this new vector we've created, QP here, and we can project it onto the normal vector. So remember what that is that's sort of the shadow of this vector QP in the n direction. So that vector ends up being precisely the one that connects the plane to the point with the shortest distance. So this vector here is given by projection onto n of QP. Okay? So that's now a connection we have. It starts on the plane and it ends at the point. Well, we're almost done now. We just need to find the magnitude of that vector, and once we've done that, what do you know? We've got the distance. So let's call this distance here, let's say d, capital D, is the distance between P and pi. Okay? Then D is going to be equal to the magnitude of this projection. Right? You might remember from the dot product section that this is also the absolute value of what's called the component of QP in the direction of n. What's more important is remembering how to compute this guy. Right? So to compute this guy, this is n dot product with QP over, so we need the absolute value of this because of the absolute value bars here. We're going to divide this by the magnitude of n. All right. So remember this here, let's move the equal signs out of the way real quick. So remember this n dot product QP, that we don't have magnitude on that because dot product is just a number. Right? Remember that. And the magnitude of a vector is always positive, so no point in putting absolute value around it. Okay, so we have to get at what is that? All right, so to actually compute this, or to write it down in terms of sort of more familiar quantities, we need to actually give numbers to each of these things. So let's say P, this point, I want to call this x naught, y naught, z naught. That's what I want to call P. Okay? And now I want to give numbers to Q. Well, let's say Q is x1, y1, z1. All right? No big deal. And for the vector n, let's do the traditional ABC. ABC. Okay. All right, so this is going to allow us to write down what D is in terms of ABC, x naught, y naught, z naught, and x1, y1, z1. Or in other words, n, p, and q. Okay? So let's continue our equation down here. Right, so n is A, B, C. Right? QP is going to be x naught minus x1, y naught minus y1, z naught minus z1. Right? And remember, we have absolute value around that. All right. We're going to divide all of that by the square root of a squared plus b squared plus c squared. All right. So that whole guy is getting to be a little messy. So let's do this. We're going to take this stuff and scroll it up a bit. Very, very quickly. There. That's better. Now we have room again. So let's continue writing this out here. So if we do this dot product, we find A, x naught minus x1 plus B, x naught minus, B, y naught minus y1 plus C, z naught minus z1. Absolute value. And of course, we still have this square root, a squared plus b squared plus c squared floating around here. All right? Well, let's continue moving these things around a bit. I want to group all the things with the sub-0, or the naughts, together, and then all the things with the sub-1 together. All right? And there's a reason for this, trust me. All right, so we have a x naught plus b y naught plus c z naught. And notice how all of the ones with a 1 have a minus sign in front. So I can conveniently do a x1 plus b y1 plus c, not c sub z, but c z1. Right. And I can stick a minus in front of all of, or I can factor out the minus from all of those. Right? This one, and this one. Okay, and now we divide again by the square root a squared plus b squared plus c squared. Okay, well, we can make this equation is already pretty great. We can make it just a little bit nicer by using a little trick. So let's say pi, our plane, had an equation ax plus by plus cz equals d, little d here. Okay? And also remember that that point Q, x1, y1, z1, was a point on the plane pi. What that means is that if I plug it into this equation is true. In other words, a x1 plus b y1 plus c z1 is equal to d. In other words, this stuff here is just d. So that allows me to do one further nice little simplification here. Absolute value a x naught plus b y naught plus c z, did it again, c z naught minus d divided by square root of a squared plus b squared plus c squared. Let's put this capital D back down here so we can put a nice box around this. And ta-da, we have a nice formula. I think this does look slightly different from the one in the book. The one in the book might have instead the equation of the plane written like this. Right? So if you write the equation of the plane like this, then of course that means this comes over as a minus d. And I'll admit that does make this formula look a tad bit nicer because this minus is now a plus. But there's not really much of a difference. And you're more likely to see the equation of a plane like this anyway. So we'll keep this and this formula here with our little minus.